Thank you very much for inviting me. And let's start out with a couple of introductions. First of all, what is MoarVM? MoarVM is a virtual machine aimed at running the Raku programming language, which was formerly known as Perl 6. Raku and the Raku compiler and the MoarVM virtual machine are all developed by an open source community. This is primarily a volunteer-driven project. There's bits of funding now and then, but not to the degree that anyone really has this as their sort of full-time job. So this is in some ways what you can do if you're a bunch of volunteers trying to build a vaguely modern virtual machine. So I'm one of the co-founders of MoarVM. I've served as the architect for it. These days also for the Raku compiler, which takes Raku source code, turns it into MoarVM bytecode. I've also contributed in some small ways to the language design, both on the concurrency and on the meta object protocol. And I work at a company called Edgement. Previously, I was doing a lot of teaching. Nowadays, my work is mostly about developer tooling projects. I was, when I got invited to this, quite amazed to realize that it's almost 10 years since we started working on MoarVM. I've learned a fantastic amount in that time about virtual machines. It's a really fun area for me to work on. Still feel like I've got an awful lot left to learn about this topic. So what I'm going to talk about today is the origins of the MoarVM project, just to put it in some context, and then look at how we started out as effectively a simple bytecode interpreter, and then over time started to incorporate what we might call the various tricks of the trade, the growing pains that we got both from what adopting those different techniques did to the architecture of the virtual machine, but also a bit about what it's like as you go from a toy language to things people start using to write production systems. And I'll finish up by talking about a new generalized dispatch mechanism that's the sort of foundation for the years to come. So the origins of the project. How did I get involved? Well, when I was a teenager, my parents said get a small job, and I didn't want to get up and deliver newspapers, so I made a web development company instead. That used Perl a lot. At university, I went to study computer science, and at Cambridge, they have some really nice courses on compilers and languages, and I really enjoyed that area. And I thought, well, after I graduated, what if I explore this a bit and see if I can help with the Perl community, who at the time were busy working on Perl 6. Yes, like Duke Nukem Forever, it was eventually released. And Perl 6 really kind of interested me. It diverged in its design from Perl 5 in many ways. And that kind of created a couple of perspectives. One was, well, it needed to. And my feeling is that Perl 6 and Raku realized a lot of the high-level goals of Perl in a much nicer way. But some people looked at it and said, is this even a Perl anymore? And eventually that led to a rename to sort of deconfuse the situation. I'm going to refer to the language as Raku throughout this talk, but that's a slightly revisionist history because a good amount of this work took place before the rename. So what makes Raku interesting to implement? First of all, it is essentially a dynamic language, but there are types, and unlike in some efforts to add types in dynamic languages where it's effectively a linter thing, the design here was always that they would be enforced at runtime at latest, and maybe you can avoid that and figure it out at compile time in the best case. So if you do a naive implementation of this, which is what we started out with, you spend loads of runtime basically repeatedly doing type checks all over the place. So here you can see add callee in the signature we do it, and then the array is typed, so that also wants to do the check as well. Another interesting thing is that operators are, except from a few exceptions, multiple dispatch subroutines. So every operation you do, like multiplication, addition, and so forth, is a multiple dispatch. This is kind of nice because it's quite regular. There's not really any ad hoc polymorphism around the operators, but it puts a lot of pressure to get the multiple dispatch fast enough and to be able to inline all of these operations if possible. Int, by the way, is arbitrary precision, and again, in a slight departure, there's also native types. So you can say, well, I want this to be a native int. It's lowercase because it's smaller, and also the syntax 4.2 defaults to rationals, not floating points. There was sort of a feeling that people would more likely be doing, say, currency calculations than scientific ones. Quite a lot of languages offer some kind of eval, that is compile time at runtime. But Raku, following on from Perl, also does the opposite. There's a concept of begin time, so you can have a bit of runtime at compile time. This is quite interesting for the Raku effort because we wanted to pre-compile code, and that means that you need to find a way of persisting all these various effects that happen at compile time. And there's a lot of metaprogramming stuff enabled by that. Just to give an example, meta classes in Raku are not just about introspection. As the compiler passes the code, it encounters a class and it creates a meta object, and then it calls methods on it to construct those types. So here there's a field, here there's a method. So we're calling methods on these meta objects, and language users can either subclass these or they can define completely new ones to define their own kinds of type as well, and then decide what are the subtyping semantics of those types, the method dispatch semantics of those types, and so forth. Raku also took the Perl idea of regexes being a first-class part of the language even further. So as we pass Raku code, we pass regexes in a single pass with that. And this regex syntax is decidedly scaling up to irregular things. We have grammars, and a grammar is really like a class, except it has, instead of just normal methods, it has rules and tokens which are written in terms of the regex syntax. And this scales all the way up to the language itself. Raku is passed using a Raku grammar. And one of the other things, there was quite a lot of enthusiasm not to fall into the trap of operator overloading, resulting in operators having strange meanings. So there was a desire to make the grammar mutable so you can find new operators, for example. And this, because the compiler, the grammar is effectively a class, changing the language is just mixing into that class. And so here we're defining a postfix exclamation mark factorial operator, and then that's just doing the reduction of the range 1 up to n. So all of this leads to a situation where the compiler turns out to be best done as just another Raku program running atop of the virtual machine, because it needs to call between the compiled code, the compiling code, and so forth. And also because the standard library and the operators are defined in terms of multiple dispatch, that means that really also ends up wanting to be written in Raku as well. Now, this sounds wonderfully elegant, but the reality is a little bit different, because when you come to implement this, you kind of realize that you're really trying to implement and define the language in terms of a language that you're still trying to work out how to run fast. So you don't just have the how do we optimize this, but also you're writing it in something that is itself not so well optimized yet. So even starting to compete with sort of a classic dynamic language implementation is pretty challenging when you're doing all of that. But I was young, naive. I had no idea of the challenges that would be implied by this. Saw a nice language, started contributing to the compiler, but was also very curious about the virtual machine. And at the time, the virtual machine that was being targeted was Parrot. Parrot aimed to be a virtual machine for all dynamic languages. It didn't really make it there, but it's been really exciting to see the same idea independently realized more recently. But Parrot, had some it was sort of an independent project, and kind of worried, well, do we want to put all of our eggs in the Perl 6 basket? Not really. And then at the same time, those of us working on the compiler were saying, well, we're kind of the main customer for this, and it's struggling to perform, struggling with threading and so forth. And what kind of happened next was, I guess, youthful arrogance. I thought, well, what if I implemented a virtual machine for the Raku language? So I decided to do that, and started it off kind of secretly because I didn't really expect to succeed. I kind of didn't want to distract from the Parrot efforts in the meantime. So just a couple of us started working on it, and it started out really as a simple bytecode interpreter. Now you might be wondering why the name, and the official answer is that I'd before this been working on the Raku meta object protocol, and we built a runtime to host that. So obviously this was putting the meta model on a runtime, so it was MoarVM. Actually, the truth is that we just really like silly memes, and so that's where the name really came from, and then we backronymed it. So the rough plan was to start out with a simple interpreter, try to make some different mistakes to Parrot at least, probably by making lots of our own, and then add the trickier things like type specialization, JIT compilation, and so on later. The architecture at the time, and the way it still effectively looks, is that we have Rakudo, and it's implemented actually mostly in a language called NQP, which originally stood for Not Quite Perl 6. It's a self-hosting bootstrapped subset of Raku, so it's written in NQP itself. And this was kind of nice because when I came to add a new backend, it was basically, and not so basically, I should really say, writing a bytecode generator for MoarVM and then getting NQP to compile itself onto the new virtual machine target. And actually, this has been done experimentally somewhat for also the JVM and JavaScript as well. So this worked out quite interestingly. I also needed to then pick a language to implement MoarVM in. That ended up being C. I knew it, but kind of more importantly, for a volunteer-oriented project, I knew there was quite a lot of people in the community who knew it more than the other options that were available. So that's what we ended up doing. The idea of trying to implement a virtual machine in some Raku subset was probably going to be a step too far. So we picked something established there. For the interpreter, I actually was influenced a bit by Parrot here. Chose a register-based design rather than a stack-based design. The interpreter started out as just using computed goto where available, fall back to a giant switch statement where it's not, and C macros to make it work across both. Why register-based? I think the original motivations that came from Parrot, one was no stack pointer to maintain. So there's sort of an idea that maybe it would be a bit quicker in that sense. Another thing is for GC marking, because we have all of the natively typed values as well as objects. And if registers have fixed types, then you just know to mark the object ones. You don't have to figure out where the native things are or keep some stack maps or reference stack or something like that. But one of the other things that I realized is that I knew we were going to try and do some of the more interesting kinds of optimization. It seemed to me like SSA form was pretty popular and was going to have a lot of benefits. And if you have register-based bytecode, it's quite a straightforward correspondence from looking at the bytecode as it exists in the byte stream or dump of that into SSA form and back again. And that felt like it would sort of make things quite understandable. There's been some downsides to this. Probably our bytecode is bigger as a result of it. I mean, it's hard to say without going and rebuilding the whole thing as a stack VM, but it feels kind of like that. The other thing that didn't seemed to be a cost but has become one is that having all these object registers, they need to be zeroed out. Otherwise, you're going to confuse the garbage collector with is this a pointer or not. And mitigating that, which we'll probably have to do at some point, is just going to get us back to the same complexity as if we'd done stack maps in the first place. So in the end, I'm not sure that kind of win actually has really completely played out. The correspondence with the SSA form is kind of nice, at least for understandability. For garbage collection, the GC hasn't really changed substantially since it was originally written. It was kind of clear to me from the start that if we were going to have the compiler as a program running atop of the VM, as well as the user program we were running, then really we had to get generational collection in from the start. The heap was just going to be too big to go walking over it, even if the program was small. The compiler is not a small program. So there's two generations. The old one is just shared, non-moving. The nursery is per thread and picks semi-space copying for that. And the GC is parallel, but not concurrent. So when we do collect, multiple threads can join in and contribute to the work, but the mutator and the collector are never running at the same time. That means, as a result of these choices, that there's some invariance. So we have to know the locations of all the collectible objects for copying. We also need to have the write barriers for generational. And when writing the virtual machine in C, that means a lot of discipline is needed. And when you say a lot of discipline is needed for something, that inevitably means it will be done wrong repeatedly. And really, we've had to find ways to try and tackle that. One of the things we found useful is to be able to run the virtual machine with a tiny nursery. That means that we trigger in failures of the invariance much more often. We also can compile in loads of assertions that we're not referencing objects from space and things like this. So that's missing updates of values. Other thing that we've found is that we can leverage existing tools to help us. So most of the time we don't go and reallocate the from space every time we collect, or the new to space, I should maybe say. But we have put in something so we can do that. And then tools like address sanitizer and Valgrind will tell us when we do reads from places that we've already freed, or that are out of date pointers. More recently, also someone's worked on a GCC plugin to do static analysis to find these problems, and that also has helped. The object system that's in MoarVM is derived pretty directly from my work on a Raku objects system, which was drawn straight from what the language design wanted. So from the point of the virtual machine, at least, a type is a pairing of a meta object and a representation. So the meta object is something implemented in a high-level language. And by that, I mean something that is running as bytecode on top of the virtual machine. And the meta object is in charge of what does it mean to dispatch a method or to invoke. What does type membership mean? It takes care of introspection and things like that. And then the representation is implemented in the virtual machine. This is taking care of memory layout and the garbage collection and serialization, deserialization of objects, because we need to be able to do that because we want to compile, but there can be arbitrary operations taking place during the compilation. Now, this is true with one exception. In the virtual machine, we provide one meta object, and the functionality it provides is just for fields, methods, that's it. No subtyping, nothing like that. Everything further is then built on top of that in the high-level language. So everything like inheritance or flattening composition of, in Raku, we call them roles. They're more often known as traits in the literature, is all implemented in the outside of the virtual machine in the language running on it. The representation is things like dynamic arrays, fixed arrays. Record types are the overwhelmingly common case. But we also have something called cstruct, which is a foreign function interface feature. And this means that folks can declare in Raku a class, and they can say, well, instead of the usual memory layout for a class, please lay it out in such a way that I can pass this to C or C++ or similar. So we have kind of O1 marshalling, which is kind of nice. Various virtual machine concepts are also modeled as representations as well. For example, continuations. So we implemented those various bits and got to a working bytecode interpreter. And in that kind of world, interpreting bytecode is kind of slow. Making calls is kind of slow. And things written in C, on the other hand, are kind of fast. So therefore, we evolved a number of ways to try and achieve reasonable performance of doing hot path things in C. So for example, a meta object could publish a flat method lookup table, and that was used for a method lookup operation. So when it didn't find it, it then had to fall back to asking the meta object. Multiple dispatch, as I mentioned, is really important. So we had a tree-based lookup cache in the virtual machine, only working on nominal types, but that would speed up a lot of multiple dispatches. Raku has first class L values. And so when you assign into something, you're always putting it into some other object. That often is a scalar container. It could be an array. But this is, of course, a very hot process as well. So the logic for that was written out in C. Now, this was kind of a little bit challenging to get right because we have continuations. We need continuations in the virtual machine to support a number of different features. Both we do essentially async await, but without the async, just the await, because we have the continuations and can take away the whole stack of things. There's also a feature for writing generators, which also is not constrained to a compile train transformation. Now, those mean that you cannot write things where you have the interpreter, you call some C code, and then it calls back into the interpreter. Otherwise, that C code is going to be a continuation barrier. So all of those had to be written in kind of CPS style as well. So that was how it started. And over time, we got to the point where MoarVM was kind of accepted as the best runtime for running the Raku language. It was faster than the various other things that had been tried at the time, even if it wasn't yet especially fast. And at this point, it was time to start doing some of the more interesting things. Now, as I mentioned, this is very much volunteer driven, so this wasn't the case that we can go and do everything right away. So I had to try and prioritize. And I made an early bet that while people often say, oh, compile it to machine code, it'll be fast, I was pretty sure that that wasn't going to be true, because compiling something that is full of all kinds of indirections to machine code is not really going to help all that much. I mean, it'll get something, but it didn't feel to me like the big win. I kind of guessed there'd be a bigger win from doing things that get rid of a lot of the dynamism and the indirections. So things like type specialization and inlining seemed to me like they would offer a better starting point and give quicker results in terms of speedups. So I started there. So I thought, oh, how do we get started doing this with what we have? And started to add what I called specializer ops. And these were opcodes in the interpreter that you were not allowed to feed to the VM in the input bytecode. The validator would complain and refuse them, but we could emit them in the optimizer, and they could do things that are safe because we've done some analysis and we've proven the properties to know that they are always a safe thing to do. So in the beginning, we started keeping counts of functions and how many times they were called. And once a function was called a certain number of times, we said, okay, we'll try and produce what I call a specialization of that. And we had essentially call site descriptors, which contain the arity, whether the objects, the arguments are of primitive types or object types. We have named arguments as well, and those exist as a runtime concept, not just a compiled away one. So we also represent those in the call site. And so a specialization would be keyed on the call site shape and the types of any object arguments. So when we decided that something was hot and we were going to specialize it, then we formed a control flow graph from the bytecode. We put it into SSA form. And then for every SSA variable, we had what I termed facts. And facts are things like we know the type of this, or we know the value of this, or we know this is what we call a type object that represents the type as a value, or it's an actual concrete instance of that type. And using the information about the call site, we could initialize these facts saying, well, we know that this is a specialization for these input types. And then we went ahead and did a bunch of optimizations. So if you know the call site shape, then you don't need to check the arity of the incoming arguments. If you know the types, then you can probably get rid of some of the type checks. If you have method lookups and they're ones that are in the method cache, then we can do those and turn them into constants as we specialize. That will get you often some branch elimination and instruction elimination you can do. And then we did some things like attribute access is normally by name of the attribute together with the class it's declared in. But if we know an exact type, then we know where in the memory layout that is, so we can just turn it into some pointer operation. That's much more quick than doing name comparisons and so forth. And we also took some of the more complex ops and tried to start turning them into lower, simpler things that would run a bit more quickly. So we started implementing these things in a branch, and I was doing this and feeding it a few simple programs and seeing some nice results, and then feeding it anything real, and it very quickly explodes because Raku has mixins. And mixins mean that the types of objects can change at a distance. So they can gain a new method. So if you have done a specialization on something, and then the object changes somewhere, then that will break. So very early on, we had to think about Deoptimization. That is going back from running the fast optimized code to running the slow path interpreter code. And I thought, well, okay, every function call that we make is somewhere that a mixin might happen that we can't locally see will happen. So that has to be a potential deoptimization point. So it built a table mapping optimized to unoptimized addresses. When we do a mixin, walk the stack, rewrite it. But once you add the optimization, this kind of changes everything, because you realize that, well, we don't just have to do it for function call points, we can do it anywhere we want. And that gave rise to being able to do optimizations based upon statistics rather than properties that we could actually prove. So we put in logging of types, so non-local variable lookups, attribute lookups, or field lookups, we might say. And if we call a function, what does it return? And if we observe that most of the time there was a stable type, then we could insert a guard for that type and then assume that type beyond that point in the optimization. Because we were producing these specializations, quite often we could then also start to say, well, we have this specialization of this function that we're calling. We know that we're calling it with these types, so we can start to get rid of the checks for whether that's a valid specialization to call and just call it directly. So this starts to get rid of some of the guards, and we start seeing that across call boundaries now, we're starting to lose some of the overhead of having to do all of these different type checks. And inlining takes that just a step further. So when the callee is small, we can inline it rather than have to do the call. That exposes more type information from the inside of the callee as well, which lets us eliminate even more of the various type guards. The main headache with doing this, I realized very early on that we had to do multi-level inlining for MoarVM, because in Raku there's a lot of places where you call a multi-sub for an operator, it delegates to a method call, and the method call might actually be very small, so we really needed to do the multiple levels of it. That meant for uninlining, that also had to be multiple levels when we do a deoptimization as well, which is a bit of a headache, but we got it to work, and it served us well to have that. We also do on-stack replacement. People love writing micro benchmarks, which tend to have some single long-running hot loop that's the whole program lifetime. And if you're doing specializations on call counts alone, then you won't ever optimize that main loop, or maybe inline everything away. So I admit I cheated. I didn't do the whole loop detection thing. I just got the compiler to spit out an op saying, "Oh, try doing an on-stack replacement here," and that just goes at the end of the loop body. Architecturally, we just reused the deopt because it's really just deopt in reverse. And eventually, somebody did implement compilation to machine code, and that was a significant win for the type math stuff. A smaller win elsewhere than the rest, and that seemed to validate the original choice. So here's just some micro benchmarks on the left, and they get less micro on the right, up to a full application doing ammonia and nitrogen calculations on farms on the right, so something relatively complex. And you can see that specialization at all is almost always the biggest win. But then inlining tends to be another significant win, and the compilation into machine code is then a little bit more based on that, especially for the micro benchmarks there. For realistic applications, it seems to be a little bit different. And the compilation result for inlining is a little bit odd because it doesn't really help. It's almost unhelping. And I think the reason for that is that the compiler is actually written in NQP, not the full Raku language, and it doesn't have all of the operators being multiple dispatch. It cheats. So it doesn't get quite the same benefits, and maybe it's not quite as well tuned there. So as we put those things into MoarVM, and as the VM started to see more real-world use, there was various growing pains we experienced. One of them is that it's very easy to put in nice optimizations that are fast and also wrong. So when these things happen, we need to find them, and we also wanted to try and detect them before our language users found them. One of the things that's worked pretty well for us is putting in a no delay mode. So instead of waiting for code to get hot, it just optimizes it all straight away. And what I expected when I did this is that this will exercise the optimizer a lot, and we'll find the optimizer bugs, and it does. But also, it also makes really, really bad choices because it has really quite limited statistical information to do all of the speculative optimizations on. So it exercises the optimization a lot as a result as well, because it normally has done all sorts of optimizations that are a really bad choice. Other than that, hunting bugs, we have lots of logging, dump the SSA before and after, dump the deoptimizations, try and have different data you can correlate. And when you look at these, one thing that I didn't think of, and then was really, why didn't I think of this, was making sure that all of the analyses and transformations in the optimizer can add comments into those logs about what they've done. So you can say, oh, why is this here? Oh, it's a result of lowering this attribute access into this simpler field access, for example. Another thing that we put in is a way to limit the number of specializations produced. And then we have a little driver program, and we can do git bisect style, figuring out which function gets specialized and then causes a breakage of some kind. And that's also been a great speed up for finding problems. Initially, we did all of the optimization work on the same thread as the interpreter. And we just interrupted it, produced the specialization, and went on. That's pretty poor use of multi-core hardware, which is everywhere these days, pretty much. The other thing was that whenever we had data parallel code, so people said, oh, go and do all of these operations across many threads on different input data, they all stampeded to try and produce the same set of specializations, and this wasn't especially good. So what we then did is, well, okay, we still need to have the interpreter logging data. So we still need to know something about sort of the call structures. So the interpreter just writes into a flat buffer, what do we call, the return values, the types that it observes as it goes. Once that buffer fills, it gets sent off to the specializer thread, and the specializer thread replay these, simulates the stack, builds up a statistics model, and then uses it to plan all of the specializations that it's going to produce. This is good in that it's a very measurable improvement. Recently, I tried to check is it still one and removed it, and yeah, it's still a big payoff. It puts another core to work as well, quite successfully, and doesn't seem to cause any particular problems in that sense. There are some issues though. One of them is that we get a new source of non-determinism in the VM, and it immediately broke our nice bisection strategy for finding bugs. So we had to put in a blocking mode to sort of recover that, where it sends its log off to the specializer and waits for it to be processed. The really ugly thing about this is that we still see some programs exhibit quite different performance between different runs, depending on other factors like timing, hash randomization, as they write into the buffer and where the boundaries of those buffers lie and things like that. And that's kind of not so nice. We win on average, but it's still not a particularly ideal situation. Another thing is that when you look at lots of micro benchmarks, it's pretty misleading because they don't really map directly to what real programs do. So initially my idea was, well, let's just set an upper limit on how many specializations we produce. And then we'll cope with the sort of rare megamorphic cases by, they hit the limit and then it just runs a bit slower. And it turns out that these aren't actually so rare, not when you get into a real application. So for example, I thought, oh, we're doing an okay job with, benchmarks, putting things into arrays and reading from them. And then in real world applications, it was pretty bad. And the problem is that here is the array class, here's the assign pos method. You never actually directly call this. It's what the indexing operator ends up compiling to. And here we have the index, which is pretty much always an int. The invocant of this method is pretty much always array, but the value varies enormously. And if your specializations are keyed on the exact type tuple, then you're going to produce, several of them and then say, oh, well, we've run out of space for specializations, and then everything else will be much slower. So in the end, we settled on having kind of 3 types of specialization, and we call them observed type, which is an exact tuple that we saw. Derived type, which is where we analyze all of the various type tuples showing up and say, well, where are they stable? Which parameter positions have stable types and which not? And that solves the problem that I showed you on the last slide, because it lets us do lots of optimizations based upon the type of the invocant and the index, but not worry about the one of the value. And then we also have certain specializations which are only based on call site shape, but not types. So that they're certain, and that you can certainly use it as long as the shape matches. But one of the things that was kind of really interesting about this is that this slide I showed earlier about the simple bytecode interpreter world, pretty much every assumption on this ended up being broken by the changes that we did. So in our new world, we compile the machine code. We can perform inlining, so small bits of code that we would call are not really a problem. And things written in C, instead of being fast, are suddenly completely opaque to the optimizer. So it can't say, oh, I know all of this type information, therefore I'll be able to lower things or make things cheaper or eliminate type checks. They were all hidden away inside of this fast path C code. So therefore, we needed to stop doing the hot path things in C. For example, assignment. We originally had the sort of workflow in C for that. It needs to often check the type of the container that it's going to assign into. But if it's done from C, we can't eliminate them. It maybe needs to trigger a call. So we have this thing called vivification of hash and array slots. So if you just look at if a hash key exists, then we shouldn't magically create it. But if you assign something into it, we should. And because L values are first class, that assignment can happen at quite a long distance from the original site where we did the lookup. So what you actually have to do is a callback, say, okay, really bind this container into the hash now because it's been assigned. And we couldn't do anything nice around that either. But the one that really caused us bother is when we came to put in some very simple escape analysis. We only have quite simple, limited escape analysis at the moment. And the write into this scalar container, which would be a really good candidate for scalar replacing, was just invisible to the analyzer. It had to say, oh, this container escapes to this complex blob of C code. So all of our speedups kind of became speed humps. Either they were just opaque to the optimizer, or we tried to abstractly interpret them in the optimizer, and that, of course, leads to its own duplication and two things to try and maintain that look like each other. The other thing is that there was always going to be way too much of Raku to bake all of the interesting semantics into the virtual machine. That was never going to scale. The cost of doing that kind of stuff in C was always going to be limiting who could implement them, and the complexity overall was a big cost. So we found that not only did we end up with various language features that were inherently slower because the VM didn't know about them, but then the optimizer came and made a really nice job of a bunch of the things that the VM didn't know about, and just made the performance cliffs even higher. So you could write two programs that only differed in some subtle way, but use a feature that was a slow feature, and then kind of suffer quite a lot from it. So the reaction to that has been to actually say, well, originally this was a virtual machine for the Raku language, and we can put all of the Raku details into it. But actually, it seems what we need is something that really is a sort of more programmable VM, so we can tell it about a lot of these language features from the outside and do that in a more sort of scalable way that lets us deal with a wider range of the language features. I kind of realized that so many things we were doing all over the place were really dispatch. And by dispatch, I just mean any operation where we are deciding which bit of code we're going to run, and it's going to be determined by the types or the values of the arguments that are going in. And what I've kind of observed is if it's a dispatch and the VM doesn't know it's one, then it's probably going to be really slow, and then the optimizer is not going to really be able to do all that much of a good job of it as well. So as I started thinking, well, how do we do this? I thought, well, maybe this is actually sort of a solved problem. This sounds a little bit like the JVM's invoke dynamic. Maybe you should look for a solution in that kind of direction. So we did that, but actually we were in a position to really take this all the way. So the VM and the compilers targeting it for the full Raku language and for the NQP subset were under our control. So rather than just adding a new dispatch mechanism, we actually removed about a dozen different ad hoc dispatchy things that have all now been subsumed by this new approach. So let's just take a look at it. There's effectively one opcode, which says, well, result is do a dispatch. We have the name, which is the name of what I call the dispatcher, which is looked up in a registry. We identify a call site shape, which is the thing I mentioned earlier. It's a specialization key. And then the registers holding the values for each argument follow. Every dispatch that we do, so long as it's successful and doesn't throw some exception in the process, bottoms out in whatever number of what I call dispatch terminals. And that might just be a constant, so some literal value we always evaluate to. It might be a value that we've read, say, as one of the arguments to this dispatch, or from a field of one of those arguments. We didn't have similar for bytecode handles, either a constant handle or one that we obtained somehow. We have something called boot syscall, and this is an entry point to calling functionality provided by the virtual machine. And most recently, we also adding the foreign function interface being mapped through this as well. Now, boot syscall is the interesting one in these, in that it's also the entry point to registering user-defined dispatches. That is, a dispatch mechanism defined in the bytecode or the high-level language compiled into bytecode itself. Userspace dispatches invoked with an argument capture. That is the argument tuple, except it has the positional and named aspects of it. It can add guards about types. It can do reads of fields and put guards on those. It can transform the capture by dropping arguments and permuting them and so forth. And then at the end, it must finish by delegating to another dispatcher, which could be user-defined or terminal. This has kind of nicely allowed us to structure a lot of the more complex aspects of Raku's dispatch semantics. For example, when we have a method call, there's various ways that you can call methods, just a boring method call, one that says call it if it exists, one that's a qualified method call identifying the parent class. Those all handled by meth call resolved. If it's a multiple dispatch method, then that forwards it to the Raku multi-dispatcher, which again has a bunch of different semantics to deal with, then goes to Raku invoke, which finally extracts the bytecode handle and sends it along to the virtual machine as a constant to run. So this is the record phase, as I call it. And after we've done all of these transformations and we've established all of these different guards across these dispatchers, then we produce a dispatch program, a set of ops that we interpret. And all of those delegations between different levels of dispatcher, all of the captures are erased, guards are deduplicated, and as this dispatch program runs, it's not doing any kind of allocation at all. It's just enforcing a bunch of guards and doing maybe some field reads and then identifying the target to go to. And this gets installed at the call site, and we can either have a single dispatch program there or pile up some polymorphic ones. And then the specializer's job is now much simpler, because instead of having to have some idea about what is a multiple dispatch, what is a method dispatch, what are all of these booleanification operations or nullification operations, now it just gets dispatch programs. It translates them into specializer ops. It gets rid of guards if it's already proven them. This is very much more regular, a lot simpler there. And we're now able to actually, it just automatically takes care of doing optimizations and type-based optimizations of things for things that we hadn't actually bothered to implement them for before, because now we just get them effectively for free, rather than having to explicitly teach the optimizer about them. This is kind of nice, but kind of a remix of ideas found elsewhere. But there's one last thing, because in Raku, dispatch can be a process over time. So here, if I have some operator base class, I have a comparison inheriting from it. We have a function called callSame. And callSame calls the next candidate. Now, in the case of inheritance, the next candidate is the next thing in the method resolution order. But we also have wrapping, where you can take a method or subroutine and wrap it with some other code that's called before it. And callSame calls the next wrapper, or eventually the original routine. It's used in multiple dispatch. You can call the next most general candidate that would match these arguments. And it's a very dynamic thing. Here also, we kind of have a process. So we have multiple dispatch here. And this is a where clause. If that where clause fails, then we need to call the next most general candidate in order to get to the general behavior, in this case of the factorial function. So dispatches may need to be continued. And due to the sort of generic, the late bound nature of the language, sorry, we don't always know up front if a call will need that. So it needs to be cheap if it isn't. We need to be able to recover the original arguments. And where we go next might be late bound. So, you know, the whole thing is potentially even stateful. So that means that we have some concept of resumable dispatches. So Userspace dispatches can optionally provide a resume callback for if the dispatch should be resumed. And they can specify resume initialization arguments, which is a set of arguments that should be made available in the case that the dispatch is resumed. For example, in a method dispatch, it'll be enough that we can recover the original invocant and the method name and the arguments. The resume callback also just built a dispatch program. It works exactly like the dispatch one, except it can recover those resume initialization arguments. And it also gets to read and write one object reference of state. And typically we're using that for a linked list of candidates. So just as an example, here we have in the record phase, we call this method, and the dispatch is to the Raku method called dispatcher, and it gets the invocant, it gets the method name, and it gets the argument. When we hit the callSame, it triggers a resume callback of the method dispatcher, which obtains the initial arguments. It does some guards to make sure that they are of the, to sort of establish that what we're going to do is founded on those types. It then builds a linked list of methods that are in the method resolution order, stores the third node onwards as the dispatch state, and then invokes the second one. We already called the first one before. That's the one we're running now. And up here, we get another resume callback that obtains the dispatch state, guards on the next method, updates it, obtains resume initialization arguments from some levels down the stack, and invokes it. Now, this is all the recording, so it's doing, again, deriving captures, adding guards. But then when we run this in following dispatches, the first dispatch just looks at the invocant type. There's no cost to preserving the arguments. They're just there in the on the stack in the argument buffer. So that's just data. This one just looks down the stack, guards on the call site shape, guards that we are really just resuming a method dispatch, reads the initialization arguments, and then runs the next method. So this is all done without any kind of allocations or things. It's just guards, reading values, putting arguments into a buffer, and doing the call. And up here, it is pretty much the same process. It's a recorded dispatch program now. So we do the guarding on the next resumption, on the call site shape, and so on. Being able to tell the virtual machine about these kinds of dispatches has been an absolutely massive improvement. Now it knows that they're dispatches. It can do an awful lot better job. The red there is the previous implementation. before we had the new dispatch mechanism, and the blue is the timings with the new mechanism. And this has really been for these kinds of features that have that continued dispatch a massive step forward for us. Not a silver bullet. We move caching at destination to caching at call site. It's good for the monomorphic majority of calls. Can be much worse. We've actually found cases of 20 times worse at megamorphic sites. So we are working on that to do a lot better. One thing that we found is that we can actually expose the number of things at the call site to the dispatcher. When it reaches a certain size, it can then install something that does a kind of slow path strategy. Finally, we also found that, yeah, warm-up is longer now. There's more setup work at every call site. And there's more to do. The dispatchers themselves are bytecode, they have to be JIT compiled and so on. So that brings us to about the end. I'd say that MoarVM has really been about trying to apply existing ideas more than creating new approaches, but I think maybe the resumable bit is something I haven't really quite seen elsewhere. But maybe someone is about to enlighten me, which will be interesting. I think in some senses, maybe we've also shown that kind of you can perhaps transition from a more traditional, if you like, dynamic language implementation to one that's doing some of the more modern VM techniques incrementally. I think maybe it does, but I don't know. There's a lot of caveats. We always had the clean separation of VM and compiler. We don't have a C extension API for the compiler. We do everything through foreign function interface or having the compiler written in the language running on the VM. And yeah, a smaller user base when we started, so we got away with a bit more. Thank you very much for listening. I hope this has been of interest, and that's what we've been doing with the VM for the Raku language. I maybe have a little bit of time for questions now.